Okay, where to begin? Let's start with the space-time element. I think that's a good place to begin and making sure we know what we're talking about. So the space-time element in flat space-time is this. This is Minkowski space. We're going to bring these back later. Um, and what we can do is call this, including this, just to sort of like clean it up. But what we can do is say like this is zero, which means the change in each angle is zero. So the change in theta, change in phi is zero, which means we're only moving radially. When we do orbits, clearly when you're orbiting, you can simplify this, but we'll bring these back. So for now, let's just get rid of it. It'll just simplify it, which means that really we're dealing with this. The whole point is that ds is the speed of light times d tau. We usually wrote this as t prime, but I'm not going to do prime. This is the proper time. And if you ever forget this, right, this is what is experienced by the moving or the local object. And what we really want to remember here is that T and R are what I call global. I don't know if that's an official term, but their T and R is time and space measurement if you assume a flat observer or an observer in flat space-time very far away, right? At infinity, which means you want no disturbances. This is what a normal observer would uh, uh, experience, right? Or a stationary observer. So this is like the stationary clock time or the stationary length measurement, right? So the proper time is like the time inside the spaceship that's moving, whereas, T is the time on Earth, right? That we consider our reference frame, our like stationary reference frame. So we say ds is the space-time, right? Traveled in space because time is a dimension of space, right? And the translator between space and time is the speed of light. So we call that d tau. So that's the proper time experienced by the moving or local object. So don't be too confused. What this really does is it reproduces that, okay, uh, right, what we end up getting from this is like time dilation, right? So we get that d tau is the square root of 1 minus v squared over c squared dt, right? So we get this time dilation equation. And I'll review, I'll say let's refer to our notes from when we derived this for that. I don't want to rederive it right now. But the point is this is equivalent to this. Right? Cool. So here's what we kind of want, though. We kind of want a few things. First of all, we need to make sure that proper time is experienced by the local moving object, which means if I did dr d tau, which we could call r dot, which we could call x1 dot, right? That is the velocity locally. That is what the object locally measures its own velocity to be relative, to its external space, right? Like that's its local. like motion, right? Cool. So that's what I mean by like, okay, xi dot could mean either x0 dot or x1 dot or x2 dot or x3 dot. When you ever see the I, it means it could mean any one of those. And if there's a lower index somewhere, it means you're summing over all of these. Well, what's x0 dot? Well, that's dt d tau, which if you do dt d tau, you get gamma, which is 1 over the 1 square root of 1 minus v squared over c squared. What's x1 dot? Well, that's r dot, which is dr d tau, which is the local velocity. And of course, x2 dot would be d theta d tau, which would be how much theta is changing over a local time. And x3 dot would mean d phi d tau. So when you see these, that's what they mean. What's cool is that this is gamma. That's the big connection. That's where I want to start. This is time dilation, right? So T dot, right, is dt d tau, and that equals gamma. That's huge. Cool. Let's just sort of pause there. But that's just notation. Like we just want to get familiar with notation. I instantly want to go to the Schwarzschild metric, right? So once we establish that, do, 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 there we go. Let's go to the Schwarzschild metric, right? And I'm going to, again, set d omega equal to 0. So we just do this. So we have c squared 1 minus rs over r dt squared minus 1 over 1 minus rs over r dr squared. And then obviously minus r squared this, but let's set that equal to 0. So we just have radial motion. So we can do one of a few things, but what I actually really want to do is this. I want to set this equal to c squared d tau squared and then divide everything by d tau squared, turning these into dots. So what this really says is that the speed of light squared equals c squared 1 minus rs over r, right? Uh, sorry, dt d tau squared, which becomes t dot squared, right? So if I divide that by that, I get dt d tau squared, which is t dot, minus 1 over 1 minus rs over r dr d tau squared, which is r dot squared. And actually, if I wanted to keep these, we could complete it. You would get minus r squared theta dot squared minus r squared sine squared theta phi dot squared, right? If you're just meticulous, you go through, you get those things. Great. Now, if I divide by c squared, which is kind of cool, I see that, all right, I can solve for t dot. So if you want to pause, solve for t dot, make this 0, right? Solve for t dot squared. What do you get? Pause it. You're now unpaused, right? You're now unpaused, and you should get that t dot squared equals 1 minus r dot squared over c squared 1 minus rs over r squared, right? So that's an expression for t dot. Now, if we solve for r dot squared, which actually might have been a better idea, right? R dot squared, right, equals, right, t dot squared plus, sorry, minus 1. I thought that was interesting, but I actually think this is more useful. T dot squared minus 1 times c squared 1 minus rs over r squared, right? So I'm just going to subtract that over, do that, and there's a negative sign there. Okay. And I could switch that around. Cool. So we have these two relationships between T dot and R dot, just from the metric. Now let's do something interesting. What we need to do is this, right? We can go one of two ways, but what we want to plug in is that value for energy from the Lagrangian, right? We defined energy as the constant we get when you have time symmetry, right? So because the metric and the Lagrangian has nothing to do with time, it's invariant with time or time invariant. There's another way to say time symmetry. We get that this constant E, right, is just dl, meaning d Lagrangian, over dt dot. And we ended up getting that that's gtt times t dot, which is just c squared 1 minus rs over r uh, times t dot. And we define that as the energy over the mass. If you want to multiply by the mass, you can get that energy equals mc squared times 1 minus rs over r times t dot. But remember, t dot is just gamma. So this is just gamma mc squared times the Schwarzschild metric adjustment. So in flat space-time, as r goes to infinity, right? E equals gamma mc squared, we reproduce Einstein's, revolution. I mean, all of this is Einstein's revolution, right? We produce normal energy mass equivalence, right? This is just special relativity energy mass equivalence. Again, all of this referred to in the Lagrangian video, but just reviewing here, just so we're consistent. Cool. So that's awesome. I'm going to write it back in terms of T dot though, because that means T dot equals energy, right? And we're going to call this just E from now on. Technically, that's E over M, right? I'm just going to call that E. Just that is energy per mass, right? E is energy per mass. That's just, easier moving forward, right? You can add the mass if you want, but just for like cleanliness, I'm gonna follow what's typically done. That's what most physicists typically do. I'm gonna follow their route just for now. But I think, it might be fun to leave the M in there to see what happens. 1 minus Rs over R times C squared. So cool, right? I'm leaving the M in there for now. I kind of like it because then you get MC squared in the denominator. I'm actually going to leave it. I'm kind of talking to myself of what I like and what I don't like. I like the MC squared in there because it reminds me of this. One way to look at it is that the energy, right, is in terms of MC squared. So you can think of like energy per mass. You can write it as E, where it really is just E over MC squared, right? Right? You might be able to think of it like that, where like the units of energy are in terms of MC squared energy, which is a very useful thing in particle physics to do. It's like in terms of rest mass energy. So we did pretty just simple algebra here. We're just looking at, pretty simple algebra. And then now what we're going to do is plug this into our equation from before, right? So if you plug this, right, into here, and you solve for r dot, again, I'll let you pause and do that, right? Plug this t dot into the r dot equation. What do you get? So pause, plug the t dot into the r dot equation and simplify it as much as possible. See what you get. I'm not sure if I want to go through the algebra right now. I'm not gonna. So you can pause, you can do it. I'll show you the end. If we need to, we can go through the algebra together. Okay, you're unpaused. Here's what you should get. You should get r dot. Um, it actually ends up simplifying. Squared, right? Equals e squared over c squared over mc squared, right? This thing. Depends on how you write it. Maybe I'll be consistent and keep the mc squared there, right? Um, oh wait, no, this is different. Sorry. I think you get, hold on. See, I've done this where you just write E as E over M. So I'm just going to write this as this. So let's be careful here. So E is just E over M. So I'm not writing the M in. And we can fill that in later if we need to. I hope that's not too confusing. But the point is you get this. This is huge. So this is the local speed, right, in proper time. It's not what's observed at infinity. That would be dr dt, and that's very different. A fun thing to do is to do something like, okay, we have an event horizon of a black hole, and somebody from infinity, some eyeball from infinity measuring t, right, sees somebody fall into the black hole. What they would see is that dr dt goes to zero, that they freeze at the black hole. But the person themselves experiences dr d tau. So they experience a velocity. The point is that both of those are interesting, but that this one becomes, I believe, more physically meaningful or more physically interesting or revealing of the space-time geometry. This is like the illusion of perspective, which is very interesting. It's like if you were to watch somebody to go into a black hole, they would appear to freeze on the event horizon, right? What ends up happening is that this goes to infinity, so dr dt goes to zero, but dr d tau doesn't. And dr d tau does something fantastically interesting, which reveals the nature of the space-time itself. So r dot reveals the nature of the space-time, not the nature of perspective. Does that make sense? Which is why I think we're going to focus on this. We could derive an equation for this. It's a little more complicated. This is also more elegant. This is a little more simple, right? Which I think is kind of cool. So awesome. Um, there's so many things we can talk about here, but here's what I want to do. So here's what you're going to do next. So there's so many ways we can go from here. This is important though. So like, yeah, let's just do this. Let's just do this. So take the derivative of this. Like pause the video, take the derivative of this. What do you get? So here's what you get, right? If you do d tau of r dot squared, and then you do d tau, it shows a different color there, not intentionally. I like that one better. Of, you know, this constant e squared minus c over c squared, minus d tau of right? C squared 1 minus RS over R, right? Keep in mind that R is a function of tau. So remember d tau of some function of R of tau, right, is the derivative of the function times R dot. So you need chain rule. Oh, sorry, the derivative function with respect to R, yeah, times R dot. Let me be a lot more clear here. F of R of tau. So many ofs. df dr times dr d tau, right? df dr times dr d tau gives you df d tau, right? And this is your f of R is this, right? Whereas this is your R of tau. Sorry if my scribbles. I hope this makes sense, right? So you have to do chain rule here, is the point. So you have to do chain rule here too, or rather, yeah, because this is technically R dot squared. So pause, see if you can figure it out. All right, ready? Pause. You're going to figure it out. Unpause. I'm going to go through it now. You should get 2R dot R double dot on this side, right? Which is kind of cool. And then where is it? I had it. There it is. Right? So you get 2R dot R double dot equals R dot. Oh, by the way, yeah, this is 0. That's a constant. And you get your R dot out front here, right? You get the minus sign, right? You get 1 minus RS over R derivative. What is that? Well, that's just, um, the derivative of 1 minus RS over R, which is obvious in um, hindsight. So we have R dot C squared times DDR 1 minus RS over R, right? DDR of this is 0. DDR of negative RS over R is positive RS over R squared, right? So we get 2R dot R double dot equals negative, right? R dot C squared times RS over R squared. Look at that. We did it. This is just from the metric and from the conserved quantity of E, right? E in relation to the Lagrangian conserved time symmetry related to T dot, right? That's where this came from. Notice what we get here. R dot cancels, solve for R double dot. Replace RS with 2GM over C squared. Aha. So we get R double dot equals negative GM over R squared. Whoa. So we actually get that R double dot is always Newton's gravitational law, even in the Schwarzschild metric, not even taking the Newtonian limit. If we went through the Christoffel symbols, we would get the exact same thing. It actually all cancels. If you write out the Christoffel symbols in the geodesics, right? If you write out the R dot geodesic and you replace E with the time dot, or sorry, you replace time dot with the E, energy from time symmetry, you end up getting the same result. But notice how you got this just via the metric itself. What I liked about this is that it included a few things. It was good practice in math, it was good practice in the notation, and we ended up getting a really cool result. I think that's a good place to pause. I hope that made sense. Feel free to rewind and go back to any of the steps. I know I skipped a lot of the algebra, but the like what to plug in and how to interpret it was kind of where I wanted to go. I feel like there's a lot to talk about here though. Like why energy per mass is, uh always conserved, what this means physically, how that interprets, but getting used to the notation of like T dot and R dot, and taking derivatives with them, I think is useful in and of its own right. So let's let those other things go. That's it.